Welcome to Mr. V Teaching Math, and to the first video in our unit on data management. Now, it just so happens that I and my students are in a Christian school. One of the things that we want to ask as Christians is how do we use math in a Christian fashion? To do that, we're going to ask three questions. First, we're going to look at what's good in God's world. We're going to look at how graphs and data work, and the ways that human beings have developed to understand and manipulate and work with data. Second, we're going to look at what sin has done, and we're going to learn about how graphs and data lie. In fact, that's what this lesson today is going to be about. The third question is about renewal. We as human beings are called to try and fix God's world, to try and return it back to what it was like before the fall into sin. So we're going to look at how to use graphs and data properly. These three questions are going to be used to structure the entire unit that we're working on. Let's begin by learning how to lie with graphs. Now I can hear some of you thinking, wait a minute, we're Christians. We're not supposed to be taught how to lie. Well, I want you to think about that. Why, as a Christian teacher, am I going to teach you how to lie and to teach you to be as good a liar as I possibly can when it comes to graphs? Think about that question while we work through this. First, just collecting the data alone, you can lie. Let me give you an example. You can ask biased questions. Here's one. Would you like your children to have to wear expensive school uniforms which will crush their individuality and creativity? Who in the world would answer yes to that? Except somebody who's terribly mean. If you ask a question like that, you are guaranteeing to get the kind of result you want. It's actually one of the hardest things to deal with when people do surveys and research and someone gives you some research and says, oh, look at this amazing research that proves that uniforms are horrible, for instance. What kind of questions did they ask in the first place? You could take this question, you could reverse it, change a few words. For instance, how would you like to have your children wear gorgeous, beautiful, inexpensive uniforms which will ensure that they are not bullied, picked on, and that they don't have to worry about spending how much money they on lots and lots of new clothing, whatever the latest styles are? Just by asking that kind of question, you're going to increase the number of people who say yes. So simply the way the data is gathered and the kind of questions they ask can bias it. A biased sample. You want to find out who likes soccer, and the only people you ask are people who are on soccer teams. That probably means you're going to get a much higher response. You should also be asking people who are on basketball teams and baseball teams and all the other kinds of teams that are out there, and kids who aren't on any teams at all, to find out whether or not kids who like soccer. So once again, you can change the data simply by who you ask. Now let's talk about some specific things that can be done with different kinds of graphs. And this is true for all kinds of graphs. Wherever I've drawn the highlighting is the key thing. In this case, they've got a title that is biased. It should simply indicate what this graph is about. Perhaps this is about barrels of oil production from a particular well. That's what it should be about. It should not use the word substantial drop. Because if you really look at this line, this isn't really a substantial drop. But simply by putting those words there, you're going to influence what people think about the data. Same kind of thing, but this time in the captions. Notice that rates finally began dropping in 1991. So they're trying to get you to think that here is where it finally started to happen. But it's not really what the data shows. Again, this kind of title should simply say years. This is the thing to watch for when you're looking at graphs. The captions and titles should be very plain and simple. They should not be an opinion. You can also manipulate the units. This is a description of the number of people who died due to AIDS, but there are no units. They just left them out. This happens in lots of graphs. How many people is this? 10 people, 20 people, thousands, millions? We don't know. The information is missing. Now this is a slightly more complex comparison. We're looking at a comparison of the number of people who prefer radios to TVs. In this case, this is the absolute number. This is the actual number of people surveyed. So 20 people were surveyed. And these are the people who prefer radio to TV. Or you can convert it into a percentage. and you can do a comparison. And these two graphs give very different results depending on what you want. Now, neither of these graphs breaks the rules. These two examples break the rules. Actually, all of these. This breaks the rule, this breaks rules, this breaks rules. This does not. Neither of these actually breaks the rules. But whether you use the actual numbers or whether you turn the numbers into percentages will change what the graphs look like and change people's opinions. In this case, you'll notice they completely left the scale out. Again, this is one of the ones that breaks the rules. And it just so happens, since I'm talking about these rules, that in the country that I live in, there are actually a series of published rules about exactly what kinds of graphs are permitted in public use. And there's a whole bunch of rules like these. Now, the only problem with these rules is that who is out there watching to make sure the rules are enforced? What you have to do is if you see a misused graph, you have to go and find somebody and you have to go complain, and then once your complaint has been put in, somebody might actually do something. It's not like that there's a bunch of policemen out there sitting there checking every single graph there is. So yes, there are rules, but there isn't necessarily any enforcement of those rules. So you need to be aware of how these things can be done. An irregular scale. On every graph, each interval or square or box or section should be worth the same amount. But notice that this goes from 0 to 5. So this is an interval of 5. From 5 to 25, that's 20 increase. And then from here to here, that's a 100 increase. And from here to here, that's an 11,125 increase. You are not supposed to make graphs that way. Your intervals should be exactly the same. Because if you took this same data and put it on a proper graph, it would look nothing like this. Your graphs must always begin with 0. There is a little symbol that you can use to show that it doesn't start with 0, but it's obviously not here. Now you need to look at what we call manipulating the vertical axis. Neither of these graphs break rules, but these two graphs are exactly the same data. Look at this graph, giant squiggly. Look at this graph, a tiny little thing here. So all they've done is change the numbers right here on the left. It's the same data, just two different graphs. They're legal, and yet they're lying to you because they're trying to convince you of something. In this case, they're trying to show you that the company is making hardly any profits at all. In this case, they're trying to show you that, hey, they're making lots of profits. Why they would do that, I don't know, but it's possible. Same kind of thing, but now on the horizontal axis. These two graphs are of the exact same data. One just has the data really close together, and the other takes the same data and stretches it out. It gives you a different feel for what's happening in the data. Once again, not illegal, but can be used to deceive you. In this case, they left a huge section of the graph completely empty. There's nothing there. You shouldn't do that with graphs most of the time. What should be done is that they actually should just go up to 40 and make the graph fit the page. By leaving a huge amount of empty white space, it gives a certain impression. For example, in this case, this graph is trying to talk about the number of people who can read in Canada. And these are the millions of people. And look how few people in Canada can read. Canada doesn't even have 40 million people in the whole country. These numbers are actually pretty good. These are reasonably decent amounts of numbers given the size of population in our country. This entire section up here is completely irrelevant because our country doesn't even have that many people. And that's the kind of thing you can do when you use blank parts of a graph. Here's another one. Your graph line should never go through the title or off the page. Even if it's drawn accurately, that should never be done, simply because it gives a certain impression of what's happening in this case. Even if the data is accurate, you should never do that. Take two graphs and compare them to each other. This one happens to be in thousands of tons, and this one happens to be in hundreds of tons. If you would look at this, you would think, oh, Manitoba is producing more lumber than British Columbia, when it's not at all true, because this is thousands and this is hundreds. If you're comparing two graphs, the units need to be the same. This is called clipping. This graph looks perfectly fine. There's nothing wrong with it, it appears, except if you include the rest of the data. Whenever you're looking at the end of the data, you should try and see, have they got the most recent data available? Now, sometimes, for instance, I'm recording this video in the year 2012, it's unlikely that they could add 2012 data to this graph because 2012 isn't over yet. Typically, it takes a year or two for data to become available. But if for some reason there's a 4 or 5 or 6 or 8 year gap, that's something you should watch for because they might be clipping their graph. Now, these next techniques for lying are specific to bar graphs. First of all, make the graphs different widths. Notice how fat this one is, all about dogs, and this one is really tiny about cats. The actual amount of space this graph occupies is many, many, many times the amount of cats. So when you look at it, your mind tells you that this is enormously bigger. But if you look at the difference, notice that there's barely any difference at all between the two percentages. Simply by making a much wider bar, you're twisting people's perspective. This is the same thing, but even worse, because now we're doing it in 3 dimensions. In reality, this one and this one are the same. They're both on this line right here, on the same line. But because we drew a 3-dimensional bar, and not only did we make it fatter, we made it extra long, this makes it seem like this is enormously bigger than this one, even though they're identical. You should never make bars that are either fatter or longer or deeper than the other ones. They should all be the same size, except for their height. Now pictographs. Same kind of thing. You should not make a pictograph in which the picture is so wide when this one is so narrow. It would be better to use a series of multiple small pizzas lined up, and then you would get a more accurate representation. For circle graphs, I have a number of different techniques. Notice the color difference. Use plain, bland, boring sorts of colors, dull colors, and then use one bright color somewhere. That's simply going to make it bigger, actually, in your perception, especially if they use red. Red has a tendency to make things appear larger to us when we do it in red. So that's important to keep in mind. Anytime you see a real contrast in colors, that's not a good thing. Different size labels. The labels should all be the same size. If you have a different size label, that suggests that they're trying to bring a particular point across, perhaps. Anytime the graph is done in 3 dimensions, the minute you do 3 dimensions, there's this little extra chunk of space that gets added that makes this appear bigger, because it's not actually part of the circle. This doesn't get any extra added, or at least not as much, while you add a whole big extra piece to the section on the bottom. Therefore, any 3D graphs are automatically deceptive. The moment you take a slice out of the graph, it increases the contrast. And sometimes, for particularly deceptive people, they'll take the slice out of the graph and then make it extra big. Now, I'm going to take you through some real-life examples of graphs that I've found over a bunch of years that I've gathered and collected here to show you how these can be used in real life. This graph I particularly like reading because it's got a whole lot of sneaky things going on inside this graph. This graph is talking about investing in education. And the idea, first of all, notice what it says in the title. Outclassed when it comes to investing in education, Canada's no prize pupil. That's a biased title from the beginning. That is an incorrect title and should not be included. Now, the rest of the graph, well, first of all, what number is this? This is 100. This isn't 0. The way this is drawn, this is trying to make it look like this is negative, but it isn't. This is 100. 0 is off the bottom of the page, way down there somewhere. So they shouldn't have started here. They're trying to, it looks like it's actually decreasing, but it's not. Now, the second, and this is important, the data is about change in expenditure. This is not about how much they spend. This is how much it's changed. So, if we take a look at where this is resting, right there. Oh, and by the way, what are these numbers? I don't know what these numbers are. They're 100, almost 100 what? Dollars? Cents? Pennies? Thousands? Millions? I don't know what it is. But let's pretend that this is, it probably doesn't make sense for it to be hundreds of dollars. So it's probably 100,000 or maybe 100 million. I'm going to guess. I'm going to guess 100,000. I don't really know what it is. But it could be a percentage for all I know. I don't even see anything that tells me if it's a percentage. But let's pretend, let's say this is, so this is about 98. This is an increase over what they spent the year before. But let's imagine, let's say Canada, just pick a random number. Let's say they increased by 98, let's say 1,000, and they were spending $100 million before. Great. We go over to Turkey, and Turkey is off the chart. Oh, look, it's right off the chart. I don't even know what number that is. I'm probably close to 165,000. So this is an increase, $165,000 increase. How much was Turkey spending the year before? Maybe it was nothing. This is trying to tell you and suggest to you that Canada is not spending enough money, but it doesn't even show you how much money Canada is spending. In reality, Canada is probably spending a whole lot more than Turkey. Maybe, but we don't know. This graph is completely deceptive. Here's another example. The biggest point is right here. Doesn't start at 0. This one is talking about general practitioners, a type of doctor. And once again, it's not starting at 0, so it doesn't really give us a completely accurate scale here on this side. Now, the age is quite okay because most people don't live beyond 65 very much, and usually they don't start becoming a doctor until you're 25 to 35. So the bottom's fine. It's nicely labeled. It just doesn't start at 0. Here we have, notice the dull, boring color in the circle graph, and a wedge that's pulled out and brightly colored. Notice also a bar over here going right off the top of the graph. I love this one. It goes up to 79%, but there's not enough room to even go to 100%. There's just not a good description of what this is about. Take a close look at this one. Notice, first of all, none of these start at 0. And they should, because it's exaggerating the change. It's making it look like there's a really big change. Now, mind you, this might actually be a pretty big change. But it would be more accurate to show it if you started at 0 and went to the top. Once again, talking about physicians, it doesn't start at 0. Again, more physicians. Again, not starting at 0. Very common not to start at 0. Off the chart. Off the chart. These ones come from the newspaper, and you'll see this rather often. It doesn't start at 0. Time and time again, these graphs don't start at 0. Now, that's not necessarily a bad thing, and there are times it's allowed, but there's a specific thing you're supposed to do for that. Again, doesn't start at 0. Again, it doesn't start at 0. What's wrong with this one? These are percentages. Really, when you're dealing with percentages, it's often actually good to go all the way up to 100 so that it's more clear. Although, you could argue that this is okay because it's dealing with interest rates. So this one's borderline. I really like this one. They stuck this nice swooping arrow in there. There should be no arrow here. This is giving you, it's trying to get you to focus on the increase. There should be no arrow, and that's fairly important. Plus, doesn't start at 0. If you actually put this graph, the increases would not be anywhere near as big as it appears in this drawing. I love this series. Because this one, I actually was standing, pumping gas in my car, and I saw this sticker on the gas pump. And I went inside and asked them if they had extras, and they gave me this one. In fact, you can even tell the backing is still on it. This is actually a sticker. But this is not as good as it could be. So they're trying to get us to focus on taxes. That's what they're trying to get us to pay attention to. And they've made some mistakes. I'd like you to think for a moment and see how could you make this a better lying graph, more capable of lying to you. Now let me show you the same graph that I pulled off the Petro-Canada website a couple of years later. This one is much better at lying. Let's go back again. Do you notice the differences? What have they done to make this a more lying graph than this one? This one's okay. Yep, this is a nice light color, and that's nice and red. But they shouldn't have pulled this one out. So now they switch the taxes to the bottom, and they pull it out. And it's red, and it's three-dimensional, all to exaggerate how big that is. It's almost like somebody actually went and sat in my math class and listened and learned how to lie. And that is how to lie using graphs. I should warn you, though, I didn't cover everything. There's actually more than that.